So now we're going to go into this review sheet, and this review sheet is really, really long. I got it I'm in this national APES teacher group, and I got it on there, and I posted a PDF of it in the course in under live learning sessions for tonight. So if you want to save that PDF or even save the link to it to try and work through it later, towards the spring, you can. It is all jumbled up on the worksheet. It's not separated by module. So I went through there and kind of separated the questions by module. So let's go ahead and get started. Okay, so the first question says, a man-made product is also known as, and this is an interesting word. I'm kind of getting tired of green, so I'm going to pick a different color to use. A man-made product is anthropogenic. Can you guys see this purple okay, or would you like a little brighter color? Okay. Let me know at any time if I pick a color that is hard to see. I chose the black background because I think it gives us more variety colors to look at, but just in case. So now we want ecological footprint. Okay, and so I'm just going to write this here. So it's the amount of, and this is like the science person definition. This might not be the definition that you would use like in conversation, but I wanted to give you the official one. The amount of land and water. This is important. You want to include water. And we kind of talked about this with our water footprint a little bit. Needed to supply a population with all the necessary resources and dispose of its waste. So that part's important too. I'm going to underline this and again. Okay, and typically more developed countries will have higher ecological footprints because they use more things, they consume more things. Okay, so let me try this one. So the equator, let's see. I want to try and do this right, but I may not get it exactly right. This is about where the equator is. And then, okay, so we did that. The Mediterranean Sea, that is, let me see if I can get you a different color. The Mediterranean Sea, oh, made it purple. Anyway, that's in there. Oh, there we go. Now it's blue. Okay. Now we want the Ogallala Aquifer. I hope I said that right. This is going to be over here. And I'm just going to call that okay. The island of Mauritius. I am not good at pronouncing this stuff. I'm sorry, guys. Let's see. Here's a pink. This island, I'm not even kidding, is right here. And the reason they care about that is because Mauritius. There's a couple of reasons. One, the dodo used to live there, and two, this island is in danger because of rising sea levels. And there's several others that are in danger, but this is one of the ones they talk about a lot. And then Saudi Arabia, let me get you that one. Some of these you guys might have like a general idea, but you may not have, I know the screen is kind of hard to see. I didn't have a black copy of this map. Indonesia, this is an island right here. The Philippines, I'm going to write this in the same purple just to save some time. There's the Philippines. Panama is over here. Iceland is up here. And it's okay if you don't know these, exactly. I'm literally looking at a map when I'm doing this, just because, geography, that is not the subject I teach. But it's good for you to kind of have an idea, like a general idea that, like, for example, the Philippines and Indonesia are in this general area. And Iceland's kind of up here-ish, that kind of thing. So that's kind of what I had that was kind of generic for the first module. In that first module too, by the way, let me just go back. This was not on the review sheet, but you will want to know, multiplying, dividing in scientific notation, and sig figs. You'll want to know addition and subtraction for scientific notation. Sig figs. You'll also want to know the scientific method, that basic stuff. I also have those study guides that I've added to the course. So you can go back to that module and you can go to the study guide, and at the bottom of it, I've got lots of like concepts and questions and things for you based on that module. So that might also help direct your studying. Hypothesis, variables, that kind of thing. Graphing. That basic science stuff that we've been doing all semester, that technically came from that module. Okay, so now we want to talk about a positive feedback loop. And the way to remember a positive feedback loop is it is something that is, it's going to take you farther and farther away from the normal condition, or like the equilibrium condition. So it's even though they call it a positive feedback loop, I think of it as a negative thing. And the reason they call it a positive feedback loop is really because, that slope is positive, but if this is normal down here, it's taking you farther and farther away. So it's kind of typically a bad thing in environmental science. So for example, we could talk about a global warming example. White surfaces, as some background, I know we've talked about a little bit. White surfaces are very reflective. Okay, so things like ice, snow, glaciers, icebergs, things like that. All that stuff is going to be really reflective, which means it reflects sun back into the atmosphere, and keeps our Earth from heating up because it's not going to absorb it, right? So as ice melts, it increases black surfaces. And if you think about like on a hot day, black surfaces are going to absorb heat, right? And this whole process is called albedo. Okay, so as they're absorbing heat, they're going to increase albedo, okay, which is then going to increase global warming. Right. Well, if the Earth is warming more, right, we're going to have more melting ice, which then is going to cause more albedo, more absorbing of that heat, which then is going to increase global warming more, which is then going to cause more ice to melt. And so you can see we're in this like it's a feedback loop, but it's getting us farther and farther away from what is considered normal or our base condition or whatever you want to call it. Okay. So our the next one is called a negative feedback loop, and a negative feedback loop is going to get us more towards where we belong. So let's say it kind of gets us farther away, and then something happens to bring us back, and then it gets us farther away, and then something happens to bring us back. So a negative feedback loop is always trying to get us back to normal or our base condition. So here's an example of one. So increasing water temperatures increase evaporation. Okay. And so then that's going to put more moisture in the air. Okay. And then when we're putting more moisture in the air, that's going to form clouds. And clouds reflect, that should be an L, more of the sun's rays. Right? Which cools the earth. Okay, so in this one, again, we're increasing temperatures or increasing the temperature for the water, which increases evaporation. Then that puts more moisture in the air, which then forms clouds. Those clouds reflect more of the sun's rays, which then cools the earth, which brings us back to normal again. And then, it's bringing us back to where we want to be, right? So as our increasing temperatures, we're putting all that's, kind of bringing us away from this normal up here. And then, forming clouds reflecting the rays is bringing us back where we wanted to be. So that's kind of how a negative feedback loop. So I like to think of a negative feedback loop as a good thing because it brings us back to where we want to go. And I like to think of a negative as a positive feedback loop as a bad thing, which is annoying because positive, that seems like it would be positive, but it's not. So now let's talk about this one a little bit. So let's talk about 3 organic compounds. Organic compounds typically are going to have carbon in them. So, you could talk about methane. And on the AP exam, you can use the chemical formula or you can use the word. Either one is fine. Hydrocarbons, I'm just going to write hydrocarbons. That was my other example. Because there's lots of different kinds. And then glucose was my other one, which is what? C6H12O6. And that's glucose. Okay. And then let's talk about some inorganic compounds. Carbon dioxide is inorganic. So you see that these have the organic ones have a carbon and a hydrogen. Hydro, that's hydrogen, carbon, carbon, and a hydrogen. Where these inorganic ones typically have, one or the other. I have nitric acid here, but gosh, if I can remember that. So I'm just going to use this one. And these are, I like to put X here that there's several nitrogen oxides that are, that we talk about in APES. And so I just put an X here and that could stand for like a 1 or 2 or whatever. And then ammonia is the other one I have in my example. And there's lots of others. And again, you can use the chemical formula or the word. Either is fine on the AP exam in your FRQ. Okay, so let me pick a color that's a little darker since we're going to come here. So now we're going to talk about these 4 elements. And remember, these are our the cycles that we talked about, the most important cycles we have. We also talked a little bit about this sulfur cycle, but these 4 are our most important. So what is carbon's importance to life? Well, it's present in all living things. I'm going to do carbon first, and then we'll go down the row. And again, if you guys have questions, please ask. The largest reservoir for carbon is rocks, although there is a decent amount in the atmosphere now. So how is carbon transported? It's all sorts, right? It can be a gas through respiration or photosynthesis. I'm just going to write photo for photosynthesis because this isn't a very big box. It can be transferred in sediments. It's moved around in fossil fuels, right? We talk about that a lot. And then the duration of the cycle. Is it long? Is it short? And carbon has a pretty long cycle time. So now let's go to the next one. Let's go to nitrogen. So nitrogen is so important. It is in proteins. Amino acids are made of nitrogen. It's in DNA. And plants need it. Plants take up nitrogen from their roots. And the largest reservoir of nitrogen is the atmosphere. If you're in APES A right now, we'll get more to this in the exact percentages when we get to the atmosphere unit. In APES AB, you may have read in the atmosphere unit that 78% of the atmosphere is nitrogen. I'm not really going to talk about the methods of transport for nitrogen because really it's in the atmosphere, and then we have some bacteria and things like that in the soil that can kind of like convert it to a biologically useful form. We can't really use the kind that's in the atmosphere. And then the nitrogen cycle, compared to the others, has a pretty short duration. The next one, let's see, is the phosphorus cycle, and phosphorus is in ATP, right? Adenosine triphosphate. That's where we get our energy from, right? It's got, if you remember from biology, it's got the 3 phosphoruses or the 3 phosphates, and we break that bond and it gives us some energy, and we make that bond and it stores our energy. It's also in DNA. The backbone of DNA is phosphate. It's also in our bones and our teeth. Okay, and the biggest reservoir of phosphorus is rocks. And this is the really important part. Remember, the phosphorus cycle has no atmospheric component. All the others do. I'm going to write no ATM here because that's kind of important. And so where do we get most of our phosphorus? Through erosion, because it's stored in rocks, and then those rocks, as they erode, and then producers kind of uptake that phosphorus and then, pass it on to the next levels of the food chain. And this is the longest because it's in rocks and there's no atmospheric component. It's just a really, really, really slow cycle. Okay. And then the last one, water. Water is a solvent. We need it to be alive, right? We need to drink it. And it also purifies things. Most of our water is in the ocean, except it's salt, right? And so we specifically can't use the water that's in the ocean, right? We have to, use fresh water, but the largest reservoir is in the ocean. And then again, all the different phases, we can use, gaseous water with evaporation. We have condensation. It's a liquid, as rain. Or other types of precipitation. Is it solid, right, with ice? So there's lots of ways that water gets around. And then water also has a pretty short residence time as well. So I know that was kind of a long slide, but we really were able to kind of get through these 4 different cycles and kind of explain the differences between them a little bit. You can kind of see that. So now we need to do the equation for photosynthesis. And what I like to tell students is either remember the photosynthesis equation or the cellular respiration equation, because they're the same thing. They are just opposite. So for photosynthesis, plants take up carbon dioxide, and then they need water, right? We all know that plants need water and carbon dioxide, and they use energy from the sun, and they make glucose, and they make oxygen, right? And that's what we breathe. Okay, now let's go to the next slide. And let's talk about cellular respiration. Another important thing to remember is that we usually think about photosynthesis as the thing that plants do and cellular respiration as the thing that animals do. But really, plants can also do cellular respiration. They take that product from photosynthesis and then they use it in cellular respiration. So, and that took me I'm not even going to tell you how old I was before I made that connection. That cellular respiration actually happens in plants and animals. And because I had that misconception for so long, I want to make sure that you guys do not. So it's the opposite, right? So what did plants make? Plants made glucose and they made water. And then they used carbon dioxide. Oh, sorry, oxygen. I'm getting ahead of myself. They used carbon dioxide and water and energy. Okay, so in cellular respiration, we're going to use that glucose, or like a sugar, basically, and we're going to use oxygen, right? That's what we breathe. And then we're going to release, right? We breathe out carbon dioxide, and then we're going to give up water. That's going to be a product is water and also energy. And then we can use that energy for whatever we need to in our bodies. So now let's do this math equation. And math is one of my very least favorite things to do in the whole world. So hopefully I get this right. Okay, so it says if the grass is on 100 hectare, and while I'm reading this, I'm just going to go ahead and underline my numbers. I may not need all these numbers, but I'm going to go ahead and underline them. If the grass is on 100 hectare acre area of grassland, grow at an average rate of 1 centimeter a day, the average volume of grass that is added to the grassland each day is what? Okay, so let's start with that. We're given 100. Okay, now, if you are going to do this on the AP exam, they will give you these conversions. Okay, they will not expect you to memorize this. Okay, so, but I've gone ahead and looked them up. Because we need to, we're going to need our answer in meters per day or something like that. They have meters cubed, right? We're going to have to go ahead and convert these. Okay, so we know that it's 10,000 meters squared in 1 hectare. So I've gotten rid of that, and I've gotten rid of that. Okay, and I know that my answer needs to be in meters cubed, right? So I need to put this in meters cubed. So I could do a separate conversion for centimeters, but I've already done it to save us some time. Okay, so now we have a meters times a meter, which is going to give us meters cubed, which is what we wanted. And we have 10,000 meters cubed per day. So that's that first thing they asked us. Okay, so now let's go to the next question. So now they say if the density of the grasses that grow in the grassland averages 400 kilograms per meters cubed, the net primary productivity is what? And that's grams per meters squared per day. Okay. So what I'm going to do is I'm going to take this answer I had from my previous part. And remember, on the AP exam, you do have to show your work. On the final exam in this course, you do not, because it's multiple choice. I'm not going to see your work anyway, so you don't have to worry about it. Okay, so now let's see what we've got. I've got 400 kilograms per meters cubed. Okay, so that crosses out my kilograms. Now I need to convert my kilograms to grams because the answer they want is in grams. So we have 1 kilogram is 1,000 grams. Okay. And then we're going to multiply this by the area of the area of, that this 100 hectare area or whatever, because we want to know for that area. So that's going to be, so I did the math earlier, and this was 1,000,000 meters squared, just so we don't have to do those conversions again. Okay. So now we're going to have 4,000 grams meters squared day. Okay. The next thing we need to do, get this, let me see if I can fit this last part. Approximately grams per day or grams per year. So all we have to do is we just have to take that 4,000 and multiply it by 365 because all the other units are the same. Okay, so that was like, that would have been probably 5 or 6 points on an FRQ right just there, because they give you a point for the work and they give you a point for the answer. Okay, so now let's talk about this next part. So evapotranspiration, and why is this significant? So sounds like evaporation. And then, transpiration is transpiration. So what's going on? This is when water is moved from the land to the atmosphere. With plants as the intermediary. So like the middleman. So the plants are the middleman, and it allows us to recycle water. Okay. Next. Okay, biodiversity. We're getting there. We're getting there. So let's identify 3 examples of biotic components of an ecosystem and then 3 abiotic components. So biotic are things that are living, right? And they are things that either are living now or used to be living. One of the examples I used to give my students in biology was like a wooden desk. That's technically biotic because it's from wood and wood used to be living. If you had a desk made out of stone, then that would not be biotic because rocks never used to be alive. So the ones we typically use are, geez, I can't even spell animals today. Are animals, plants, bacteria, and I'm going to use fungi too because they're also living, and that'll cover basically almost all of our bases. And then things that are not living are soil. Now, technically, there's living organisms within the soil, but the soil itself, is made of ground up rock particles, and so soil itself is not living, but there are living things in there, like that top layer with the humus and stuff. Water, rock. Those things are not living. Onward. So let's match the following. So these are different organisms, and some of them we've talked about, some we have not. But we want a generalist. A generalist is something that will eat lots of things. And so of these choices, um, they like the rat to be the best one. I would maybe use the alligator too, but I guess there's a better one for the alligator. Okay. A specialist, something that's going to be very particular in what it eats. It's only going to eat that one thing and then not really anything else. So the panda would be a good example of a specialist. Another one would maybe be like a koala. An invasive species. We've talked a little bit in the water module about zebra mussels. We maybe have mentioned kudzu. I think we've talked about. Trying to think of another one. There's one called the green mussel, but that's not super common. It's just one that I used to work with. A keystone species. This is a species that's going to have an impact in the ecosystem larger than what you think. Okay, and this is the one they like to use the alligator for. We've also talked about otters as keystone species and wolves. Both of those are good keystone species. An indicator species is typically going to be an amphibian because amphibians, because they kind of like breathe through their skin a little bit, they are really sensitive to changes in the environment. So the salamander would be a good indicator species because it's an amphibian. And then an endemic species is a species that lives in one location and really nowhere else. And so a Galapagos tortoise would be a good example of an endemic species. Okay, so now let's talk about the term biodiversity. And the best definition I've ever really heard about biodiversity is the variety of species. Okay, it's not the total number of organisms in the environment, it's the variety. So let's say, for example, This is kind of a weird example, but let's say we have donuts, right? And these are all glazed donuts. We've got a lot of donuts, but they're all the same. So the diversity of donuts is pretty low. Okay. But let's say here we've got, like sprinkly donuts, and we've got, this cream filled one. And then we have, like a regular donut. And then we've got one with like lots of icing on it. Um, I don't know the other types of donuts. There's like a swirly one, that looks like a braid or whatever. That's a donut, whatever. So you've got lots of different types of donuts. So this box of donuts is going to have a higher variety because there's lots of different ones. Okay, so if these donuts were animals and this box was their environment, this box of donuts would have a higher biodiversity than this box of glazed donuts because, the glazed donuts is just glazed and it's, just the one thing. There's still a lot of them, right? In fact, there's more glazed donuts in this box than this box because I ran out of types of donuts to think of. But that one's the one with all the different kinds is still going to have a higher variety. So it's going to have the diversity is higher. Biodiversity. So now let's talk about populations. Okay, so let's draw a graph, and we're going to put time on the x-axis and population on the y. Okay. If we want to talk about linear growth, it's going to be a straight line. And then if we want to talk about exponential growth, let me use a different color. Exponential growth is going to look like that. Okay. So let's go onward. The 4 most populated countries in the world. We have China, India, the United States, and Indonesia. Onward. Okay, so the rule of 70 is something we use to find the doubling time. Okay, and it's a really interesting little equation. I'm not really sure, whoever came up with it, it was really smart. Sorry, this should be the growth rate. I'm all excited about doubling time. Okay, so we have R is equal to your growth rate. And it's usually expressed as like a percentage. And so to do the rule of 70, you just do 70 divided by R, and that'll give you the doubling time. Okay, and you should have this memorized for the AP exam. They won't give you this formula, and they may expect you to do it. Okay. So let's do a doubling time problem. This city has a population of 50,000 in 2012. If the population grows at an annual rate of 2%, the year in which the population will reach 100,000 is what? Okay, so that's the doubling time, right? Because it's, double of 50,000 is 100,000. So we'll just take 70 divided by 2, and that gives us 35. And then we'll add 200 or 2012 to it. So we'll get 2047. Okay. And then the rate in which the year it will reach 200,000 is the same. We're assuming it has the same growth rate. So that would be another 35, which should be 2082. So you see all these numbers and percents, and it looks really, really hard. And then, you can use that rule of 70 problem, and it's easy peasy. As my son says, easy peasy, lemon squeezy. I think that's from a video game. Now let's talk about this one. A population was 12 million in 1992. And in 2012, it was 24 million, right? It's doubled. So if the population grew at a constant rate, what was the percent rate of growth? So the first thing we need to do is we need to do 2012 minus 1992. And of course, I didn't do this math. I think it's 20 years, but I want to make sure. Yes. Okay, so remember, our doubling time was 70 divided by R equals the doubling time, right? So now we need to find the growth rate in a percent. So we can take that R, multiply both sides by R. We have 70 equals 20 times R. We can divide both sides by 20. And we'll get 3.5. Not too bad. Okay, now let's define some of these population words. Okay, the total fertility rate is, this is an estimation of the average number of births a woman will have in her lifetime. And it's different in different countries. The total fertility rate is different in the United States than it is in, say, Nigeria. Okay, so the replacement level of fertility is the average number, that's a number, not a hashtag, of children a couple must have to replace themselves. And interestingly, it's usually just over 2 because they have to account for the fact that like some die. So it's usually just barely over 2, like 2.1 or something like that. The infant mortality rate is the number of infants out of 1,000 who die before their first birthday. It's a sad word, a sad term. And again, it's going to be different for different countries. Typically, more developed countries are going to have a lower infant mortality rate than less developed countries because they have better medicine and care for pregnant women and things like that. The crude birth rate is the number of live births per 1,000 annually in a population. Again, this is different per country. Your crude birth rate in China is going to be different than your crude birth rate in Nigeria. And then your crude death rate, same thing. And usually your death rate goes down as you become more industrialized for the same sort of reasons. As the infant mortality rate goes down, you have more health care and things like that. Education, sanitation, that kind of stuff. Okay, so let's go on. Okay. So now let's draw a logistic growth, and then we're going to do the carrying capacity. So this is going to be time again on the bottom, and this is going to be population size on the y-axis, and then our graph is going to look like this. And you can see it kind of looks like an S, which is why they call it S curve. And then right about here is going to be our carrying capacity, and this is kind of where it levels off. And interestingly, carrying capacity, even though it starts with a C and it has two C's, it's abbreviated with a K. I don't know. Okay, so this one says, in a particular year, a population has the following characteristics. The birth rate is 45. The death rate is 20. The immigration rate is 1%. This is immigration. That means they're coming in, I for in. And the emigration rate, it's actually pronounced the same way, but sometimes I call it emigration. And it's E for exit. So that means they're leaving. And the percent rate of growth is, okay, so for this one, we need to do crude birth rate minus crude death rate divided by 1,000, and we'll get R. Okay. So let's see. We have now the one thing you have to do, you have to kind of keep in mind for this is let me write this a little better. I didn't really write it very great. Let's try it again. I like to write it better this way. So we have our crude birth rate plus our immigration, because those are things that make the population bigger. And then we'll do crude death rate minus the immigration plus the immigration. Those are the things that make the population smaller. And then we can divide that by 1,000, and that'll equal R. Okay, so let's kind of do this math a little bit. So I'm going to write that a little smaller. So we'll do our crude birth rate was 45. Our immigration rate is 1. And it's 1%, so that's going to be a 10. And then our death rate is 20. And our immigration rate is 0.5%. So if 1% was 10, then 0.5 would be, 5. Okay, so then we'd have 55 minus 25 divided by 1,000 equals your R. Now, when you put this in your calculator, make sure you do your parentheses like this. Okay, so then you'll have 30 divided by 1,000. I'm going to go backwards. If any math teacher is watching this, they're going to freak out. Okay, 3 over 100. That's 3%. You're likely not going to get such pretty numbers on the AP exam because they do allow calculators now. And so they do that so you can't, the reason they did that is not to make the problems harder, but to be able to use more realistic numbers. Okay, so this is why I did not, this diagram, it's hard to see. So let's see. We want to draw the demographic transition. So we'll have 1. So we'll have these 4 phases. And this one is pre-industrial, transitional, industrial, and then post-industrial. Okay. So now let's draw, let's make our birth rate pink. Okay, so in the pre-industrial, the birth rate's pretty high. In transitional, it starts to kind of go down. And then industrial, it's down. And then it gets even lower in post-industrial. Okay, now let's make, I'm going to call this the birth rate. Now let's do another color. What do we want? Maybe red? No, red is too close. Let's try blue. So now let's do the death rate. We'll make that blue. And in this pre-industrial, these are kind of, they're going back and forth, right? And it takes, the death rate tends to sink first because in this transitional, we're getting improved healthcare, medicine, and all that. And the death rate and the birth rate tends to stay higher because, it's that like population momentum kind of deal. And then sometimes in a post-industrial society, the death rate will actually increase over the birth rate, which means you're going to get like a negative population growth. Okay. And I can kind of show you on the next one kind of what that negative growth might look like. So here's what we're going to do. We need to do we have slow, rapid, this is really fast, negative, and 0. And these are our population pyramids. Okay. So if we're going to have slow growth, each one of these is going to have like kind of a, I like to draw the rapid first, actually, if that's okay. And the reason I like to do that is just for scale. So in the rapid, you're going to usually have like these really wide bars. And then at some point, it kind of like gets skinnier towards the top. Okay. So slow growth is going to be, similar. It's just not going to be as wide, and I'm not doing a very good scale here, but kind of like this. And then a negative growth, you're going to have something like this, where you've got fewer people in those childbearing years than you do in the older generation. So this you might see in a country like Italy, because remember at the bottom, you've got your like kids. Kind of towards the middle, you've got childbearing years. And at the very top, you have, old people. And I guess you could have middle age in between, but basically these three. And then 0 population growth, you're going to kind of be like, it's going to kind of be the same all the way up and down. And this is not even, usually this line would be in the middle. I just didn't have a lot of space. And then again, still when you get to the top, just this one too, it's going to get skinny. And that's because, eventually, old people die. So it might look something like that. Okay, so now onward. Now we're going to talk about survivorship curves. So we're going to talk about early loss populations, late loss, and constant loss. Okay. So in early loss population, they're gonna have lots of babies, but they're gonna die really quickly. Okay. So this is things like mosquitoes. A lot of times, invasives, some fish, some amphibians. And this is where they have lots of babies and then they die and only a few survive to adulthood. The other type, the other really common type is that they they have a high survival rate as they're older, but they're not going to have as many babies. And this is type 1. That one's green is kind of hard to see. So this would be like large mammals, elephants, humans. We don't really have typically a lot of babies at once. And then right in the middle, you have what they call type 2, which makes sense, right? And this is kind of they have a consistent death rate at all ages. And birds are typically a good example of this. Okay, now this is kind of a hard graph to see, but we have percent of girls enrolled in secondary school and then the total fertility rate. So this is basically saying the more likely you are to go to school, the less likely you are to have children. Because, the more girls that are in school, their fertility rate is much lower. And so that's why they say that like educating women is one way that we could reduce the population. Okay. So let's talk about R-selected versus K-selected species. R-selected species typically are very tiny, which is not one of the choices here. One of the things they like to do, but they are typically smaller. And they have many offspring. So they are like a type 3. We talked about that just a couple slides ago. And they have short or no maternal care, which might be why their babies die so much. And then K-selected species tend to be large, typically. And they have few offspring. So we see them a lot in type 1 survivorship. And they tend to have a lot of maternal care, which is why their babies don't die so much. But it's also why they can't have so many babies because their mamas would go crazy, right? If they had hundreds and hundreds of babies. So they just do a couple at a time. The very end is terrestrial biomes. And the term biome is a terrestrial region, although technically we can have biomes in the ocean or aquatic biomes, but we'll go with it. Terrestrial region defined by inhabitants and climate. So typically, there's these areas of the earth that have similar climate, which means temperature and rainfall, and they tend to have similar plants, which then attracts similar animals. So what determines the type of biome? We talked about that. It's the climate, and your climate is your temp and your rainfall. And what determines your climate? Your geography, where you're located on the planet. Okay, now let's talk about a couple types of forests. We have three different types of forests. We have this tropical that we're going to talk about right now, and then we have a tropical rainforest is obviously going to be in the tropics. It's going to have high temp and high rain. It's going to have a dense canopy of plants. And it's going to have lots birds, insects, amphibians, mammals, and it has high biodiversity. Remember when we talked about biodiversity, that is the variety. Okay, next. The deciduous forest. That's going to be in areas kind of like those mid-latitudes, kind of where we live. And you're going to have defined seasons. And you'll have moderate rainfall. These places are going to have deciduous trees. It's nice they have deciduous trees and it's called the deciduous forest. You never would have guessed that, right? Undergrowth, shrubs and things like that. You're going to have deer, hawks, foxes, owls, etc. And then the last type of forest that we're going to talk about here is the taiga, which is the boreal forest. That's going to be really like northern latitudes. Here it's very cold, and they tend to not have as much rainfall. We're going to have conifer trees. These are ones that make cones. And we'll have mooses and bears, that kind of stuff. Now let's go to the next set, and we're going to have a couple different types of grasslands, and then we'll talk about the desert. Okay, so the tropical grasslands, those are going to be found, obviously, in the tropics. And these are going to be hot, but they're not going to have a lot of rain. And so they can't support a lot of trees. So they're going to have like tall grasses and some trees, but not many. And this is what you think about of like the African savanna, right? And when you think about Africa and you think about like the lions, giraffes, zebras, elephants, that kind of thing. Okay, the temperate grasslands, it's going to be, again, those mid-latitudes, but it's going to be in mid-latitudes where maybe you're not going to get as much rain. So we're going to have seasons, but moderate to low rainfall. And here you'll have grasses and small mammals. Okay, then we have the tundra, which is like a cold grassland. It's not going to get as much rainfall as like the taiga. Um, and it's going to be cold almost all the time. And so you're not going to get a lot of plants here, maybe like lichens, some things like that. And it's because you've got permafrost, which means the the soil is totally frozen. Sometimes the top layer will thaw a little bit in the summer, and then it freezes right back up in the winter. So there's not a lot of ability for plants to grow. You'll see polar bears, seals, other coldy animals, caribou. And then the desert. And then we have 3 different types of deserts. We can have a tropical desert. We can have a temperate desert. And we can have a polar desert. But basically, they're all dry. The only difference is really the temperature. Oh, man. This plant went here. And these animals went here. Oh, well. So the plants in the desert, we're going to have succulents. And then you have like lizards, snakes, but it's really going to vary by the type of the desert. For example, you may not see a lot of lizards and snakes in the polar deserts. Okay, so let's do something else. We're almost done, I promise. A rectangular area forest measures 10,000 meters by 300,000 meters. So it has an area of what? So we have, what do we have? 10,000 times 300,000, which is going to give us, that's what that, 9 zeros, 3, 4, 5, 6, 7, 8, 9. So I like to write all my zeros, and then I write my commas. So that's going to be square meters, and then we'll have to convert that to kilometers. So I'm going to call that 3 times 10 to the 9 meters squared. Now, this is really important. There are 1,000 meters in 1 kilometer. That's just going to get rid of one of our meters, right? So we need to do that again. That will give us square kilometers, okay? So that's going to give us 3 times 10 to the 3 kilometers squared. And then again, if we wanted to turn this into hectares, we'll take 3 times 10 to the 3 kilometers squared. Let's see. And so let me fix this. If we want to convert this to hectares, so the conversion I have actually is in meters. So it says that there is 10,000 meters squared. And so let me do this math, because the conversion I had was incorrect. 3 e to the 9 divided by. Okay. Okay. And then our very last slide. Whew. Let's talk about some countries or places where we might see some of these biomes. Okay, so in the taiga, you might see this in Russia or Canada. The tropical rainforest in the desert would be um, Northern Africa, which I know is not a country, but some of the countries in Northern Africa are Libya, Egypt, Nigeria. Okay. A temperate grassland, you'd see these in the United States. We have those here. And they also have those in China. Tropical grasslands are in the Congo. A temperate deciduous forest, we also have those in the United States, right? That's kind of where we live. Our temperate deciduous forests in France. And again, the tundra would be Russia and Canada. Okay, so that's the end. That's our first 4 or 5 modules of AP Environmental Science.